takeoff distance performance calculation. As students, understanding how to calculate takeoff distance is crucial for safe and successful flight operations. Key factors affecting takeoff distance. So what affects takeoff distance? Let's break it down. Number 1. Weight. The heavier the aircraft, the longer the takeoff distance. Number 2. Density, altitude. Higher density altitudes means thinner air, which increases takeoff distance. Number 3. Wind. Headwind decrease takeoff distance, while tailwinds increase it. Number 4. Runway surface. Different surfaces like grass or asphalt affect takeoff distance. Number 5. Aircraft configuration. Flaps, slats, and other configurations impact takeoff distance. Sample performance calculation. Now let's walk through a sample calculation. We'll use a Cessna 172R with a weight of 2,500 pounds, taking off from a 3,000-foot asphalt runway at a sea level with a 5-knot headwind. To determine the aircraft takeoff distance chart, interpolate the chart to find the takeoff distance at the given weight and altitude, and apply wind correction. Step 4. Calculate the adjusted takeoff distance. Using the chart and applying the corrections, we get an adjusted takeoff distance of approximately 1,200 feet. So why is this calculation important? It's all about understanding the core principles of flight mechanics and pre-flight planning. Lift and drag. Takeoff distance is affected by the balance between lift and drag. Thrust and weight. The aircraft thrust must overcome its weight to achieve takeoff. Pre-flight planning, accurate takeoff distance calculation ensures safe operations, help pilots prepare for unexpected situation. That's it for today's topic on takeoff distance performance calculation. Remember, understanding this calculation is crucial for safe and successful flight operations. Always plan ahead and happy flying. For a jet engine, thrust available or TA significantly decreases with increasing altitude because there is less dense air entering the engine, which reduces mass flow. Imagine a graph with thrust on the vertical axis and velocity on the horizontal axis. As altitude increases, the TA curve shifts downward, indicating lower thrust at very velocity. Thrust required or TR at a given true airspeed is primarily determined by the drag equation. D equals 1/2 rho v squared SCD. While air density rho decreases with altitude, the effect of reduced TA is the most critical change in performance. Even though TR also decreases with lower density, the drop in TA limits the engine's ability to produce thrust, affecting overall aircraft performance. The drag family tree illustrates how total drag breaks into parasite and induced components. Parasite drag includes form, friction, and interference drag, while induced drag stems from lift generation and the resulting downwash and winding vortices. Now, consider the thrust available and thrust required curves versus speed at varying altitudes. As altitude increases, air density drops, causing the thrust available curve to shift downward across all speeds. The thrust required curve given by D equals 1/2 PV2 SCD also falls with density, but the reduction in thrust available is the dominant factor affecting performance. Next, examine the thrust available and thrust required curves versus speed at different aircraft weights. When weight rises, induced drag increases, pushing the thrust required curve upward, especially at lower speeds. Thrust available remains unchanged, so the speed for minimum thrust required moves to a higher value. Finally, the physical sources of various drag types are shown. Wingtip vortices and downwash illustrates induced drag, rivets, surface roughness, and skin friction represent parasite drag elements. These visual together clarify how drag, thrust available, and thrust required interact with altitude, weight, and the underlying aerodynamic phenomena.